Hello and welcome to lecture 52 of the course Theory of Computation. This is also the first lecture in week 11 of the course. In week 10, we saw the notion of NP completeness. We saw Cook-Levin theorem which showed that SAT was NP complete. We also saw some other languages being NP complete, which was CNF-SAT and 3-SAT. Right? We also saw properties of NP completeness, some other properties. In this week, week 11, we are mostly going to be seeing other NP complete problems, right? So we will make use of what we have already learned, and using those properties we will see other NP complete problems. Hopefully the idea is you'll understand different types of NP complete problems, like how so many different types of problems can be NP complete, and also the different ways in which we can build gadgets in order to show NP completeness reductions, right? So the first problem that we'll see is CLIQUE. In fact, all the ingredients to show that CLIQUE is NP complete we have already covered, right? So it is just about stating them, putting them together and seeing that it is NP complete, right? So CLIQUE is the problem of we are given two things. One is a graph G and a number K, and this is a yes instance if the graph has a clique of size k, right, or bigger. So this is NP complete. So clique is a subgraph, right? Let's say it has, let's say k is 4, means there are 4 vertices such that they are adjacent in all possible ways, right? So there are 6 possible ways in which 4 vertices can be adjacent to each other. So all these possibilities exist. If there is a 5 clique, there is a group of 5 vertices which are adjacent in all possible ways, right? So again, my drawing is terrible, but it's messy, but you get the idea, right? So this is NP complete, right? So how are you going to show that this is NP complete? So we are going to make use of the following observation that we saw from the previous week. So to show that SAT is NP complete, we had to show that all languages in NP are reducible to SAT. However, from now on we are not going to be taking that route, because we already have one NP complete language. In fact, we already have SAT, CNF-SAT and 3-SAT. All of them are NP complete, right? So what we are going to be using is this result. Like we saw that suppose B is NP complete, C is in NP, and B is reducible to C in polynomial time, then all of these 3 together imply that C is NP complete. So the way we are going to do this is take an existing or take a known NP complete language B, and let C be the language that we want to show is NP complete, right? So then all that we have to do is choose a NP complete language, choose a known NP complete language B, then show that B reduces to C, right, where C is the language that we want to show as NP complete, and then show that C is in NP, right? Or we could change the order. We could show that C is in NP and show that B is reducible to C for some NP complete language B, right? So the things that we have to do is to show that CLIQUE is NP complete, we have to show that CLIQUE is in NP, and then show that an existing known NP complete language reduces to CLIQUE. So here we choose 3-SAT. So we will show that CLIQUE is in NP and 3-SAT reduces to CLIQUE. In fact, both of these we have already done. In lecture 48, again in the previous week, we showed that 3-SAT reduces to CLIQUE. We had a full reduction. So when we saw NP complete polynomial time reductions, right? So this shows that 3-SAT is in CLIQUE. So now all that remains is to show that CLIQUE is in NP. In fact, even this we have already seen when we were seeing lecture 30, where we showed that CLIQUE has an n non-deterministic decider, right? So all that we do is we guess a subset of vertices, right? So how do we guess a subset of vertices? Guess means to non-deterministically select a such set of vertices, right? So you go to vertex 1, you either non-deterministically decide to select or not select that. Go to vertex 2, do the same thing. You non-deterministically decide to select or skip that vertex. 3, non-deterministically decide to select or skip that vertex, and so on. and at the end you have a subset of vertices, right? We have a subset of vertices, and now you just check, is a set of size, does the set have size k? If the set has size k, we continue. If it does not have size k, we reject, right? So that's first step. So we have chosen a set non-deterministically. If it does not have the desired size, we reject. If it has the desired size, we check whether it is a k-clique or it is a clique. Like we have already checked whether it has size k. We check whether it is k-clique. We, for each pair of vertices, check whether there is an edge. So the A here, Aij is one, A here is the adjacency matrix. So A is the adjacency matrix, right? So if any such, for any ij, Aij is 0, or in other words, there is no edge between I and j, then we reject. If all of them are adjacent, we accept. Right, so this we had seen then, and it's clear that it's a non-deterministic process, right? So the time taken to non-deterministically select or omit each vertex is the number of vertices n, and then we have to once we have that, then for each pair we check whether for each pair we check whether whether there is an edge, right? So that takes so k squared time. So k squared is at most n squared. Hence, hence this whole process take at most order n squared time, right? So this takes order n time. Maybe I'll mark that here. This takes order n time, and this takes order k squared time. Right, and so the whole time, the time complexity of this entire process is order n squared, which is polynomial. Hence, so we had already seen that this is a decider for clique. So I am not going through the correctness, but this shows the running this shows that the running time is also polynomial. So that the correctness we had already seen. The running time being polynomial is very clear, and hence this is a non-deterministic polynomial time decider. Hence, clique is in NP. And earlier in the last week we showed that 3-SAT reduces to clique. Together these two imply that clique is NP complete, right? So that is one more language that we know now to be NP complete. Now if we want to show a new language is NP complete, we can reduce from clique, right? We can add clique to the arsenal of languages that we have, and so that we can reduce from clique, right? The next thing is vertex cover. What is vertex cover? So in an undirected graph, a vertex cover is a subset of vertices, right? So here the vertex cover is a subset U, right, of vertices, such that all the edges, there is some all the edges, one of the endpoints is in U, right? So if you take this graph here in the left side, the circled vertices, the circled vertices form a vertex cover, right? Because you take this edge, there is this endpoint in this edge, both endpoints are there. This edge one endpoint, this edge one endpoint, this edge one endpoint, this edge one endpoint, and this edge also one endpoint. So usually we are interested in the smallest vertex cover. Clique, we are usually interested in the largest clique. Right? So vertex cover means it's a covering problem. We want to cover as many as possible, but we want to reduce the number of vertices used in covering, right? So while this is a vertex cover, now if we can add one more vertex also, that's also a vertex cover, right? So you can add any vertex because already it is covering. So one more vertex will continue to cover, right? So that is the vertex cover, and here on the right side we have a complete bipartite graph. 3 vertices on the left side and 4 vertices on the right side. So any half we can take, or the right side or left side, and that forms a vertex cover. So these 3 vertices form a vertex cover. These 4 vertices also would form a vertex cover or form a vertex cover, right? But then I just mark this because this is smaller in number. Okay. So the problem, the language vertex cover is the following: is a set of pairs G comma K, where G is an undirected graph with a vertex cover of size K. Right? G is an undirected graph with a vertex cover of size K. So this graph and number 3 we will accept. This graph and number 4 also is a yes instance, because it has a vertex cover of size 3, it also has a vertex cover of size 4. This graph and 2 we will not accept, because if you look at it, there are no 2 vertices. So in fact 2 vertices will not make a vertex cover, because to cover this triangle in the left side itself we need 2 vertices, right? Because and then 2 vertices from the triangle, so then that would mean this edge is uncovered, right? So we need a third vertex. So G2 will be a no instance, right? So that is the language. So give graph and a number K such that the graph has a vertex cover of size K. So this is yet another language which is NP complete. So we saw SAT, 3-SAT, etc., which were languages based on Boolean formula, which were NP complete. And now we are seeing CLIQUE, which is just based on graphs and whether there exists a CLIQUE of a certain size. And now we are seeing vertex cover, where we have a graph and we are asking whether there is a vertex cover of certain size, right? So this is a different flavor of NP complete problems, right? It also shows that like how like different types of problems can be NP complete, right? So we are going to we are going to follow a similar approach, where we just have to, if you do the following, if we do the same thing as we did for CLIQUE, we'll do the following. We'll show that vertex cover is an NP, and then we'll show that a known NP complete language reduces to vertex cover. So the known NP complete language is going to be 3-SAT, right? So in the book it is theorem 7.44. Okay. So the first part, this part is easy. Vertex cover is an NP, and usually the hard part is the second part, to show that an NP complete language reduces to the vertex cover or any. So if you are trying to show that the language C is NP complete, reduction from a known NP complete language to C is going to be usually the harder part. To show that C is an NP is usually easier, right? So here also we will do the same thing as we did in CLIQUE. We can do a guess and verify type argument, right? We can guess a subset of K vertices, right, and check whether these K vertices constitute a vertex cover, right? So in other words, whether these K vertices cover all the edges, right? So this is the straightforward algorithm, and it can easily be checked that this is a polynomial time algorithm and it's an autodeterministic algorithm. Hence vertex cover is an NP, right? So this is fairly straightforward, so I'm not going to spend further time on this. What we are going to spend further time on is the reduction from 3-SAT, right, which is somewhat interesting, right? We are going to spend time on the reduction from 3-SAT, right? So what do we mean by reduction from 3-SAT? Given a 3-SAT instance phi, we want to build a vertex cover instance gk, right? Given an instance phi, we want to build gk such that phi is a yes instance of 3-SAT if and only if gk is a yes instance of vertex cover. In other words, the formula phi is satisfiable if and only if G has a vertex cover of size K, right? This is what we want to build. And the second thing is that the process of coming up with the vertex cover instance, coming up with GK, this should also be done in polynomial time. In other words, I am saying the reduction should be completed in polynomial time. So given phi, you should be able to spend polynomial time and come up with GK such that phi is satisfiable if and only if G has a K sized vertex cover. Okay. So let phi have n variables and m clauses. Okay. So this is phi is a 3-SAT instance, so it's an AND of m clauses where each clause is an OR of 3 literals, right? So something like this. So here we have a rather simple example so that the figure does not become too messy. So we'll have repeated variables and all, repeated literals and all that. But whatever the procedure I am going to describe is fairly general, right? So you can any 3 CNF formula we can build a corresponding graph, right? So what we are going to do is, given phi, we are going to explain how to build G, right? So G is very simple. So suppose this is phi, right? x1 or x1 or x2 and x1 complement or x2 complement or x2 complement and x1 complement or x2 or x2. Okay. So we have 3 parts. One is that, so there are 2 types of vertices. One is the clause gadgets. So this corresponds to clause C1, clause C2 and clause C3. The shaded parts are each one clause gadget. So we have 3 clauses here in the formula. So we have 3 clause gadgets for the first clause, second clause and third clause. So each clause gadget is 3 vertices. So C1 contains x1, x1, x2. C2 contains x1 complement, x1 complement, x1 complement, x2 complement, x2 complement, and C3 contains x1 complement, x2 and x2. Okay. So each clause gadget contains 3 vertices labeled with the variables or literals in the clause, and these 3 vertices form a triangle. And then we have variable gadget. So this is variable gadget for x1 and this is variable gadget for x2. This is even simpler. So each variable gadget consists of 2 vertices, x1 and x1 complement, here x2 and x2 complement, and they are adjacent. They are connected by an edge. So variable gadget for xi contains 2 vertices, xi and xi complement, and connected by an edge. Right. So I have told you about the clause gadget and the variable gadget. Now how do we connect them across the clause gadget and variable gadget? So the vertices are over. What remains is the edges. So, and some edges I have already mentioned. So in a clause gadget, all 3 vertices are connected. So each clause gadget contains 3 edges and 3 vertices. Each variable gadget contains 2 vertices and 1 edge. Right. Now what remains is, the vertices are over. What remains is the edges going across. This is very simple. You look at a clause gadget and you see which are the literals. So you see x1, you connect it to the x1 in the variable gadget. In the variable gadget, x1 appears exactly once, so you connect it. So x1 you connect it, x1 you connect it, x2 you connect to x2. Here it's x1 complement, so you connect to x1 complement, x2 complement connected to x2 complement, and continues. And same thing for C3 also. So this completes the construction of the graph. So G is complete. This completes the construction of G. Now all that I have determined, so now to get the instance, all that we have to do is to determine K or tell K what K is, right? So this is explaining whatever I just said. 3 vertices form a clique and 2 adjacent vertices in the variable gadget, and these are the new edges. We add edges between the vertices in the clause and the variable gadget that have the same label. And as I said earlier, if phi has n variables and m clauses, the variables being x1 to xn and clauses being c1 to cm, then G has 3m plus 2n vertices. 3m plus 2n, because each clause gadget contains 3 vertices each. So m clauses gives 3m vertices, and each variable gadget contains 2 vertices. So 2n vertices in all. So we get 3m plus 2n. So total number of vertices is 3m plus 2n. Total number of edges is also not very different. We have each clause gadget contains 3 edges. Each variable gadget contains 1 edge. So 3m plus n edges, 3m plus n, and then further these edges, there are again 3m edges. So I think I made an error here. So it is I think 6m plus n, I think, because each clause contains 3 edges. So 3m, then n edges, 1 for each variable gadget, so 3m plus n, and then again 3m edges going across, so 6m plus n, I think. Maybe I'll just say check so that you can check and verify this. So this is the graph. The graph is polynomial size, 3m plus 2n, 6m plus n, and it's the procedure is fairly simple. Like, given the formula, the process for constructing the graph is simple. So hence the construction of the instance is also in polynomial time, right? So you can write a for loop or something for the clause gadget, for the variable gadget, and for the edges going across, right? So we can construct the graph in polynomial time. Finally, what is our k going to be in the vertex cover instance? K is going to be 2m plus n. Notice the number of vertices is 3m plus 2n, but k is going to be 2m plus n, right? So the construction is going to take order m plus n time, I have already mentioned, and so it is polynomial time. This you can verify. I have already explained, but you can also verify. All that remains is to show the following: the correspondence. The formula is satisfiable if and only if the graph has a vertex cover of size k, which is 2m plus n. So how do we show that? The formula is satisfiable if and only if the graph has a vertex cover of size 2m plus n. Okay, so suppose the formula is satisfiable. Maybe we can explain with the help of this particular instance, right? So is this formula satisfiable? So setting x1 to be true satisfies the first clause, and setting x2 to be false satisfies the second clause. But then x1 is true and x2 false, then the third clause is not satisfied. So we have to take another strategy. So let's say we set x2 to true, that also satisfies the first clause. And since x2 is true, we set x1 to false, that satisfies the second clause. And then third clause also satisfied, right? So the one satisfying assignment is x1 to false and x2 to true, right? So now we have two directions to show, right? One is that if the formula is satisfiable, the graph has a vertex cover of size 2m plus n. The other is the opposite direction. If the graph has a vertex cover of size k, which is 2m plus n, then the formula is satisfiable. So first let us go see the forward direction. If the formula is satisfiable, the graph has a vertex cover of the set size. So in this case the formula is satisfiable, right? x1 is false and x2 is true, right? Now since x1 is, so now I'll explain how to pick the satisfying assignment. So maybe I will use a different color to pick them. Maybe I'll use this color. So x1 is false, so we pick this x1 complement from the variable gadget. x2 is true, so we pick x2 from the variable gadget. So we pick these two, and for each clause we know of at least one true literal, right? So in the case of clause 1, we know x2 is true. Clause 2, we know x1 complement is true. Clause 3, we know both are true. Let's say x1 complement is true, right? So what we do is we select the vertices which are not the true, which are not the ones that I just mentioned. So in clause 1, x2 is true, so we pick the other two. So what I'm building is the vertex cover, right? So the formula is satisfiable, and from the satisfying assignment I am building the vertex cover, and these circled vertices are going to be part of the vertex cover. Clause 2, x1 complement is a true literal, so we select the other two, clause 3, in fact all the literals are true, but let me pick x1 complement as the true literal, right, and the other two are the ones that I pick. So the claim is that this constitutes a vertex cover. So let us see why, right. So one thing is that from each clause gadget, right, each clause gadget we have picked 2, right. So whatever I am saying is I am saying on the basis of this particular example, but it is general. Even if you construct any from any formula phi, if we from any 3 CNF formula phi, if we construct this reduction and we follow these rules, whatever I am saying applies for any such instance, right. So we have picked two vertices from each clause gadget, right. So the claim is that this clause gadget has 3 edges, and these 2 vertices, any 2 vertices in this triangle covers the edges, right. So all the 3 edges here are covered by these 2 vertices. So all the vertices in this clause gadget is covered, and all the vertices in this clause gadget is also covered, and all the clause gadgets, all the vertices in all the clause gadgets are covered. Sorry, all the edges in all the clause gadgets are covered by the 2 vertices that we picked from each clause gadget, right, because the 2 vertices cover this triangle. Now all the edges in the variable gadget, right, so variable gadget just consists of 2 vertices and 1 edge, that is covered by the single vertex that we have picked from each variable gadget, right. So all the edges in the variable gadgets are also covered. So what remains to argue is the edges that are going across, right. So for each clause gadgets there are 3 edges coming out of it, right, one from each endpoint, one from each vertex of that clause gadget. So 2 vertices are anyway covered because they are anyway 2 edges coming out of the clause gadget to the variable gadget are anyway covered because so if we take C1, these 2 edges are anyway covered because these x1 and x1 are part of the vertex cover. So the only thing that remains to be argued is this x2 or this edge, how is that covered? This edge is covered because this x2 is covered, and in a general setting we have one edge that is to be covered, but how did that edge or how was this vertex chosen, or how was this vertex x2 in the clause gadget chosen to be not included in the vertex cover? This was chosen to be not included in the vertex cover because it was a true literal, right. So we looked for, in every clause we looked for one literal that is true. So this was a true literal and hence it was not part of the vertex cover. So which means it is adjacent to the x2 in the variable gadget, which is a true literal and which will be selected. So if this x2 is true, then it would be adjacent to a vertex in the clause gadget, in the variable gadget that is selected as part of the vertex cover. Hence that explains how this edge is also going to be covered, because this x2 is not part of the vertex cover only because it is a true literal, and because it's a true literal, this endpoint is going to be part of the vertex cover. Hence these edges are also covered, right. So I have said the same thing here. Choose a true literal from each variable gadget and add them to the vertex cover. So S is the vertex cover. The true literal from the variable gadgets covers the edges in the variable gadget. Choose a true literal from each clause gadget and add the other 2 vertices into S, right. And because we are picking 2 vertices from each clause gadget, this covers the edges in the clause gadget. What remains is the edges going across, right. From each clause the vertices from the class gadgets and the true literal from the variable gadgets cover them, right? So if you look at this clause, there are 3 edges coming out going to the variable gadget. These 2 are anyway covered. What remains is this, and this x1 complement was not picked because it was a true literal, which means the other endpoint must be selected. So that covers all the edges. Hence the selected vertices form a vertex cover. And how many vertices did we select? 2 from each class gadget, so 2m, and 1 from each variable gadget, so n. So we pick 2m plus n vertices, and that forms a vertex cover. So we started with the assumption that there is a satisfying assignment, and we got a vertex cover of size 2m plus n. Right? So this completes one direction. Now for the other direction, suppose the graph has a vertex cover of size 2m plus n. Suppose the graph has a vertex cover of size 2m plus n, right? Now we need to show that there is a satisfying assignment. So let's try to see this again. This graph has a vertex cover of size 2m plus n. Now notice the structure of this graph. There are these m class gadgets. Now if I need to cover a triangle, right? If I need to cover a triangle, something like this, maybe I'll do it below. If I need to cover a triangle, like this, these 3 edges, right? We need to pick 2 out of these 3 vertices, right? So any class gadget, we need 2 vertices at least in the vertex cover. So any class gadget, we need at least 2 vertices coming out of it, and any variable gadget, right? It is something like this. To cover this edge, we need to pick one of these endpoints, right? So we need 2 vertices from each class gadget, and we need 1 vertex from each variable gadget at least to form a vertex cover, right? We need 2 vertices from each class gadget and 1 vertex from each variable gadget. So this itself tells us that we need minimum 2m plus n vertices in a vertex cover. But here the assumption was that there is a vertex cover of size 2m plus n. Now this and now we are saying that every class gadget has to have at least 2 vertices and every variable gadget has to have at least 1 vertex. Now the only way we can do this is to pick exactly 2 from each class gadget and exactly 1 from each variable gadget, right? Because if we pick more from one class gadget, that means some other class gadget or variable gadget will not get this number, and hence there will be something that is not covered in that class gadget or variable gadget. So this implies that the vertex cover contains exactly 2 vertices from each class gadget and exactly 1 vertex from each variable gadget. Because if you try to pick more from some class gadget, some other gadget is going to suffer because of that, and hence it will not be a vertex cover, right? Which means we picked every class gadget contributes 2 and every variable gadget contributes 1. Now it is kind of the same argument that we saw in the other direction of the proof, but in the reverse direction, right? Now how is this going to be a vertex cover? So now every class gadget picks 2, so the edges in the class gadget are covered, and edges in the variable gadgets are also covered by the 1 vertex. Now how are we covering the edges going across, right? So if you pick a class, 2 edges are covered because 2 vertices are covered. The third vertex is covered because the third vertex is covered, third edge is covered because from the other side, from the variable gadget, right? Because we only have exactly 2 vertices from each class gadget in the vertex cover. So the third edge going across is covered by from the literal side, sorry, from the variable gadget, right? Which means if we set all these selected literals to be true, so x, in the case of x1, suppose the vertex cover contains x1 complement, then we set x1 to be false. In the case of x2, suppose we select x2, so then we set x2 to be true. So we look at each variable gadget and see which literal is selected for the vertex cover. So if xi is selected to the vertex cover, you set xi to true. If xi complement is selected to the vertex cover from the variable gadget, we set xi to be false. And this ensures that this assignment that I just described. So you look at the selected variables, selected literals from each variable gadget, right? So maybe I'll just write it again here. So suppose some xi complement, here xi is picked, so we set xi to true. Now suppose some other, let's say xj complement, then here we set xj to, so I'll use another color just for, set xj to false. Right, because set xj to false. So depending on which one we picked, and as I just explained, this will ensure that the selected vertices will form a vertex cover. Sorry, selected vertices will form is a vertex cover. So the selected literals, the way if we set it this way, this assignment will form a satisfying assignment. This is because every so we need to argue that every clause has a true literal. So the way to argue this is that the look at the variable or look at the vertex that is not picked into the vertex cover from the clause. The claim is that this will certainly be true because this is not being covered from the clause vertices, this edge is being covered from the other side, which means the other side means this x2 is connected to x2, so the other side means x2 should be picked, which means x2 should be set to true. Hence each clause is satisfied, hence the formula is satisfied, right? So this gives us that each the assignment that is constructed like this forms a satisfying assignment, and since phi has a satisfying assignment, this implies that this is a yes instance of 3-SAT, right? So maybe I'll quickly summarize since we have said a lot. We first show that vertex cover is in NP by a guess and verify argument. Second, we want to make the construction. We want to show that 3-SAT reduces to vertex cover. So given a 3-SAT instance, we want to construct a G and K such that the formula is in 3-SAT if and only if the graph G has a K-sized vertex cover, right? So we have this clause gadgets and variable gadgets. So each clause gadget contains 3 vertices, one for each literal in the clause. Each variable gadget contains 2 vertices, one for each literal, xi and xi complement. And we also do this cross connections by connecting each vertex in the clause gadget with the vertex in the variable gadget with the same label, right? And the claim is that this graph has a 2m plus n vertex cover if and only if the formula is satisfiable. If the formula is satisfiable, what we do is we take the satisfying assignment and we pick the true literal from each variable, and true literal we pick that from the corresponding variable gadget, and this will set at least one literal from each clause to be true. So from each clause we pick two vertices that may not be said to be true, so excluding one that is set to true, right? And this forms a 2m plus n size vertex cover, which we argued. And similarly, if we have a size 2m plus n vertex cover, we first argued that it has to have exactly two vertices from each clause gadget and exactly one from each variable gadget, and the one from each variable gadget tells us which variable to set to true and which variable to set to false, and these together form this forms a satisfying assignments, right? And that completes the both sides of the correspondence, and that implies that if the formula phi is in 3-SAT if and only if the constructed instance gk is AS instance of a vertex cover, which means G has a k sized vertex cover where k is 2m plus n, right? So recall this, that we have to show that some NP complete language reduces to vertex cover, and here we had chosen 3-SAT. But in the beginning of the lecture we showed that CLIQUE is also NP complete, right? So another way would have been to show that CLIQUE is reducible to so in place of 3-SAT reduces to vertex cover, we can show CLIQUE reduces to a vertex cover, right? So that is the final remark that I want to make. So instead of showing 3-SAT reduces to vertex cover, it's also enough to show that CLIQUE reduces to vertex cover. So just think about how we can reduce CLIQUE to vertex cover. So in fact we can reduce CLIQUE to something called independent set, and then independent set can reduce to vertex cover. So independent set is a subset of vertices such that it's like the opposite of CLIQUE, such that none of these vertices are adjacent to each other. So it's a set of k vertices such that none of them are adjacent. Any pair ij, it should not be an edge. So the language is, given a graph G, is there an independent set of size k? Are there k vertices such that none of them are adjacent pairwise, right? So this, I think you can look up what the meaning of independent set is. Maybe I'll just say this. Maybe I'll just write it here. A set of k vertices such that no two are pairwise adjacent. And the language is independent set gk. G has a k sized independent set, right? So this you can reduce CLIQUE to independent set and then independent set to vertex cover. So this you can try out as an exercise. And that completes lecture number 52, where we saw that CLIQUE is NP complete as well as vertex cover is NP complete. So now we have seen two languages which are entirely based on graphs and not on Boolean formula that are NP complete. And in the next lecture we will see yet another language that is NP complete, which is it's also going to be based on graphs, but a different property. Here we are looking for a certain structure in both CLIQUE and vertex cover. In the next one we'll be looking for a certain type of path in a graph. So see you in the next lecture.